section, which is at the top right hand side of your screen. If you could add that there, and we'll try and get to them at the end of each of the presenters if possible. And also just to let everybody know that we are recording this, so if anyone's got any objections, if they could let us know, that'd be fantastic. And to start today, I will throw it over to Gemma Wyburn from Australian Pork Limited, just to have a very brief introduction as to why the industry has been involved in this project. Thanks, Gemma.
Thanks, Janine, and hi, everybody. It's my pleasure to introduce this webinar on the collaborative project that we have been engaged with, looking at black soldier fly and its abilities to manage agricultural waste from the animal industries. I guess pork has been a lead in this project. We have project managed it from the grant side of things, and we got involved because we saw an excellent opportunity to leverage this, I guess, emerging technology around insects and understanding the potential that they have in helping us to reduce our waste and potentially benefit from other products that can be generated from the insects. It does lead on from earlier work that we have done in the space, where we looked at black soldier flies as well. But primarily, I guess for us, the exciting part of this technology is just to see what we can do to improve our circularity. Goals in the space around reducing waste to landfill to zero. And we believe that these insects can play a pivotal part in helping us to get there. So thank you for coming, and I'm now going to pass on to our Sasha Jenkins from UWA to kick us off.
Hello everyone, welcome. I'm going to just give you some overview of the project before we get on to some of the experts. So this is Closing the Loop, Black Soldier Fly technology to convert agricultural waste into valuable co-products. It's a collaborative project between industry, academia, consultancy and government, and our partners along the bottom there. I'm just going to give you an overview of the project in this slide. So Luke Wheat at Future Green Solutions, he basically spent most of the project optimizing the black soldier fly larvae, rearing them on a various range of different livestock wastes. His main objective was to basically reduce the amount of waste volume, and he was able to actually get it up to 70 to 80%. He's going to tell you a bit more about that later. So obviously our main objective was to reduce the waste, but after we've reduced the waste, we're left with two co-products. The first co-product is the insects themselves, which are basically the larvae, which are rich in both fatty acids and proteins. The fatty acids are extracted and they can be used for other things like biodiesel and plastics. Whereas the protein, it can't go back into the food chain because we've basically fed the larva manure. So we need to look at another way of utilising that product. And essentially that's where Dr. Matt Redding has come in from DAF Queensland, and he'll talk a little bit later about how he's taken that protein and developed a fertiliser from that larva meal. The other co-product from this is actually the larva frat, which is essentially fly poo. And this is also rich in mineral nitrogen and carbon. And what we at UWA, what we were looking at is basically developing that product as either a soil fertilizer or soil improver. So that was the focus of my team. There's also Dr. Margaret Kratt, and she did the whole economic and market analysis as part of this project. And then we have our collaborators at Scalexia, with Janine being the lead. And they looked at the environmental and biosecurity risks of the larva and the larva meal, and also in relation to regulation. And finally, Dr. David Cook at DeepHerd, he looked at stable fly emergence because we really wanted to make sure these co-products weren't going to present a risk of increasing stable fly emergence. So overall, the objectives of the research is to develop the black soldier fly technology to come up with a sustainable livestock waste management option to rapidly reduce the waste volume and quite significantly. The second objective was to then look at the larva protein and also the frass, the co-products, to develop them as low-cost tailored fertilizers or improvers. C was to also look at quantifying the biosecurity and environmental risks associated with applying the frass to cropping and other parts of the production cycle. And D is to investigate the market potential of the black soldier fly products. And finally, to look at overcoming some of the barriers to adoptions, particularly around biosecurity risks, environmental regulation, and also public perception. So I'm now going to hand over to Luke, who's going to tell you a bit more about how he's managed to reduce the volume of waste.
Thanks, Sasha. Okay, thanks, Sasha. Thanks, Gemma. I want to start by just quickly acknowledging the traditional owners, past and present, and the land on which we all operate. I'm calling in from Wajak Noongar Wujak today, which is Perth and the Swan Coastal Plain. And I also just want to echo Sasha and Gemma's comment around this project being a really broad cross-section of the agricultural industry in collaboration with some, super skillful and multidisciplinary researchers. I think it's a great collaboration. It's probably the biggest that we've seen in this emerging industry domestically. And my hope is that that encourages more research of this type across industry and within industry, particularly for the insects as we grow together. It's a really exciting space, and it's good to see so much support coming from the agricultural sector across Australia. So I'm Luke Wheat. I'm founder and CEO of Future Green Solutions. We're a commercial insect producer based in Western Australia. And really my role, or my company's role in this, was to look at how we adapt our existing technology onto agricultural waste streams. First of all, I'll give you a quick background of what is the black soldier fly. There's probably a lot of people on the call and within the agricultural industry who are still unaware of insects and what they are. The black soldier fly, although a close cousin to those more pest flies that we're all used to in Australian agricultural operations, is a non-pest fly. Its larvae is a non-select feeder. They're very ferocious feeders and super efficient at converting organic waste streams into valuable products like protein and oil, as well as the soil amendments that Sasha rightly mentioned. So the adult is a non-biting fly. They're not considered a disease vector because they don't feed in their adult form. And probably the next point is that when we think about the culture of these insects, they're not free range. It's all maintained in a super controlled environment. So high level overview, I think something to point out is that insects, while a different species, in terms of our farming practices, are very similar to what you guys are familiar with in pork and dairy and poultry and other farming systems. The only difference being that we have sort of hundreds of millions of head of livestock under one roof at any one time. And again, we're doing things under a very controlled environment. So not too dissimilar to all of the other agricultural processes that you're familiar with. Much more rapid life cycle, and we only need to maintain about 1% of our total population to support a stable population. So very efficient in terms of breeding efficiencies. Future Green Solutions, our mission is to give waste a purpose. And so, as Sasha mentioned, depending on the waste streams that we use to rear our insects will dictate the end markets to which we can sell our products. So our current business model focuses on using clean organic waste streams, that is, waste streams that do not utilise manures and farm mortalities. And that allows us to sell proteins and oils back into for livestock, aquaculture and pet nutrition as an ingredient for feed manufacturers. We also produce fresh products for agriculture and horticulture, as well as support a growing industry with seed stock in the form of fly eggs. So our role in this project was really about understanding how we take what we know about clean insects and their performance on clean substrates and moving that across to tackle more problematic waste streams, if you like. So this was a really different a really different approach to future green solutions, because the substrates that we're dealing with as agricultural waste typically very poor in nutrient, low digestibility, particularly on the waste streams such as paunch, which are very high in lignocellulose. And so you can imagine the performance of the insects on manures is far poorer than what we're used to on clean substrates, which have a much higher nutrient density. And so the challenge really was, how do we take what we know about insects and their behaviour and their nutritional requirements and amend our farming practices to give us a greater outcome on digestion? And we did that through moisture correction, adaptation of larval feeding rates and stocking densities, substrate pre-treatments, and we tried that included enzymatic treatments, physical sort of particle reduction, and a number of other testings that we tried to try and increase the digestibility, as well as increased exposure time. And there was several iterations of those experiments to optimise over the 3-year trial. Some of the substrates were very hard just off the bat as a single source, but as you're aware, farms will often have more than one source of waste. So, for example, the pork manures, we had a combination of the separated solids, as well as farm mortality and manures on straw or other bedding. And similarly with the egg layers, we had the farm mortalities again, so the birds, the manures, and waste egg and protein from their manufacturing producing facilities. But overall, great outcome. By the end of the 3 years, we've managed to bring the waste reduction volumes in line with what we experienced with our control substrates, so it's complete clean substrates, where we achieved 80% or more reduction in waste volume in a matter of weeks, which is far more efficient than traditional composting, which can take months. A much reduced greenhouse gas emissions and much lower odours, as well as the production of the value soil ameliorants, which Sasha's touched on, and I know her and Matt will touch on in much more detail soon. They had some really exciting results from those. I might just point out that the dairy accumulated solids performed much more poorly than the fresh manures. And for those that are unfamiliar, the accumulated solids are dairy manures, particularly the separated solids, which have been stockpiled on farm for several months. So if you imagine, they're more of a already get composted product, so there's not much nutrient left in there for the insects afterwards, and the volume had already been significantly reduced before we brought it into the rearing system. The paunch was particularly problematic, again, because of that high lignocellulose. And so future research is probably needed to understand how we break that down into something more digestible for the insects. Overall, that's very promising results from using insect technology as a manure treatment. We had significant and rapid reduction of waste volume, clear reduction in stable fly emergence. So in Western Australia, and I believe parts of the East Coast, stable fly is a pest fly. It's a blood-dependent fly, so it's one that will bite and causes millions of dollars damage to livestock, and it's particularly prevalent in areas where livestock and horticultural operations are adjacent. So the larvae will establish in manures that have been applied to horticultural land, and the insects will feed on the livestock in adjacent properties. So David Cook from the Department of Agriculture in Western Australia ran some trials where we used raw poultry manures and poultry manures that had been processed by the insect farming. And we found that once the frass was applied back onto the land, there was almost no stable fly emergence at all, which is a massive win for the local industries. Soil ameliorants, again, Sasha will dive into more detail on the crop benefits, but really improved crop health and growth performance, great increase for drought tolerance. Matt Redding, again, some really cool research going on the East Coast using larval-based extractions for fertiliser formulations. And again, reduce greenhouse gas potential compared to business as usual. So in closing, I think it's been a really exciting project. There's been some really good partnerships. Future Green really pride ourselves on having good long-standing partnerships with collaborative researchers and within industry. And I think this is going to form a really good basis and a platform to launch new research and new collaborations moving forward. Thanks very much, guys. Back to you, Sasha.
Is there any questions before we move on to Sasha's? Not at this stage. Okay, Sasha, take it away.
Sorry, it's Jeremy here. Yeah, it's a reminder that enter your questions into the Q&A tab at the top of your screens, and we'll deal with the questions at the end of the presentations. Thanks.
Thank you. So now I'm going to provide a bit more information about how we develop the frass as a soil amendment. So as I said from that first slide, this is this part of the cycle. So we're interested in looking at the larva frass, which is essentially fly poo, and turning that into some kind of organic fertilizer, whether it's a fertilizer or whether it's more of a soil improver. So the objectives of this specific part of the research was develop frass as a low-cost, tailored, slow-release, granulated fertilizer or product that's safe to handle, store, transport, and also apply. And we also assessed any biosecurity and environmental risks associated with applying the frass to cropping. So methodology was looking at a whole range of pot and field trials to look at how frass performed from different industries on different crop species, so horticulture, grains, but also pasture species. We then did a series of soil incubation experiments, and these were really to try and understand how the frass, mechanism of the frass and how it worked. So those were very targeted bits of research to try and untangle how the frass is benefiting the plant. As Luke mentioned, we also looked at greenhouse gas emissions, and we did extensive pathogen testing, and David Cook did a series of field trials looking at stable fly emergence when we added frass to the soil. We also then looked at whether we needed to, depending on the product of frass or which industry it come from, we then looked at where we needed to granulate it further or further process it. And in some cases they had like quite a lot of ammonia, so we had to slow that down. So we were coating it with some of that fatty acid extracted from the insects. So as Luke mentioned, one of the key findings is that we reduced the volume from 70 to 80%. But we also saw in the field trials and the pot trials, we saw a demonstrated reduction in pathogens. So this is just this first table just shows shows some of the decreases we're having in the fecal coliform counts. So we've got the pork, boiler, and layer and dairy waste products. This is the initial manure waste that was loaded. So we can see that's pretty high in fecal coliforms. And then we re-examined the coliform count in the larva and the frass derived from feeding the insects, those manure types. And we can see there was a reduction in all of them, some more significant than others. We also looked at, David Cook looked at a whole series of field trials, mainly in horticulture, looking at seeing if we could reduce that stable fly. And these were in areas where we have known stable fly issues, and there's a stable fly ban in those particular shires. So at the low application rate, between 1 and 5, which is kind of what the recommendation we're kind of applying them, we just didn't see any stable fly emergence. Only really we started to see the emergencies when it got high, and we really wouldn't be applying at those rates anyway, but even still it's pretty low. The other key findings is we did a series of, as I said, like big field trials and also pot trials looking at horticulture species, pasture species, and grain species. And this first plaque shows the frass at increasing concentrations of frass application. And we've got red, clover, ryegrass, wheat, and canola. So I think you can see, looking just at these photos, that as we add more frass, we're getting a much greater yield in yield of those crops. So what we found is that the frass does supply nitrogen. So it can be used as a partial N replacement. It can't fully replace N fertilizer, but it can certainly reduce the amounts of fertilizer the farmer would need to apply. One of the other exciting findings we found is that the frass itself behaves, when we apply it to soil, it ameliorates some of the soil constraints on plant growth. One of them is still soil acidity, so it basically raises the pH of the soil. So and our soils are pretty acidic over here. The other thing is we did a series of trials where we were water stressing, both in field trials and pot trials, where we pot them deliberately under water stress, so droughting them, to see how well they responded if they've had been amended with frass. So this is one of our, so on the right hand side, got the little pot trials, and this is showing black soldier fly applications at 0 to 20% volume volume. And it's showing the response curve to drought. So these plants have been droughted, and we can see as we increase the amount of frass we're adding, we can see that the plant is able to withstand and resist that water stress. So that's pretty exciting. Other things we found, particularly in the field trial, we saw an increase in carbon. So this first graph shows carbon against increased rate of frass, and you can see there's a steady increase in the carbon in the soil. The second graph looks more towards the greenhouse gas reductions. We saw a reduction in odour, greenhouse gas, and also nutrient leaching. The second graph shows this one of the figures or from the nitrous oxide. So we've got nitrous oxide against time. Two things that we want to look at is the blue dots, this one here, which is basically the manure, and the yellow is the frass. And I think you can see the frass reduces the greenhouse gas potential by up to half. It's dropped by half there. So it is a significant reduction there. Finally, we looked at granulating to reduce transport costs, and there's a picture of the granulated product there on the far right. So what does this mean for industry? So obviously Luke's talked about the improved waste and waste disposal and reducing the waste. So that's improved waste management and a sustainable way of doing it and a quick way of doing it. The second thing is increased productivity and probability. So we're generating new products and then we'll have new markets for them. We also are potentially going to reduce the on-farm costs associated with waste management, and if the farmers are using fertilizer use as well. Reduce biosecurity risk. So big thing is it's obviously reducing the pathogens compared to manures. And we've also got a reduction in that stable fly and other nuisance flies. So it wasn't just stable fly, it was other nuisance flies were also significantly reduced. And that will, particularly in WA, that will help us regain some of those markets lost, particularly in the horticulture areas in those shires where we're not allowed to, because of the Stable Fly Ban Act, they're simply not allowed to stockpile or even apply manures to those soils. And finally, we saw enhanced soil health benefits. So we saw obviously a decrease in greenhouse gas, but we also saw this improvement in soil health in terms of carbon, beneficial microbes. It obviously can provide some plant nutrition. It raises the soil pH and also helps the plant deal with become a bit more water efficient. So continuing on, what other opportunities might there be? So one of the things we talked about with some of the farmers that other potential pathways for the frass and the larva, because they don't all want to turn it into fertilizer. So it looks like certainly from the literature that it would be both the frass and the larva will be a good substrate for AD if they were looking for more of a waste to energy solution. There's also parts of it have been used, the chitin and other parts have been used in developing bioplastics and cosmetics. So there are alternative pathways if they're not interested in the soil. So that's one area we could look at. Other areas are further evaluation of the frass in terms of the soil amendment, restoration, rehabilitation. It's basically looking at sites where the soil is poor and see if we can actually bring that back into production. And finally, full life cycle analysis needs to be done in relation to the greenhouse gas emissions, and then obviously in terms of carbon. So just looking at the whole cycle to see if we do get a reduction across the whole production cycle. Oh, that's it. So I'm going to then hand over now to Matt, who's going to give you a bit more information about how we looked at the protein and turning that into a valuable fertilizer product.
And Matt, just unmute yourself, please, Matt.
Yep. Okay, so you can hear me now?
Yep.
Good. All right. So yeah, I'm Matt Redding. This part of the project, as you've heard previously, was about using larvae as fertilizer. So proof of concept study in a way in that regard. However, the larva has some characteristics which I think are really interesting in terms of the ratios of carbon to nitrogen in these materials. And they're sort of, they've condensed down the nitrogen into a smaller mass. I've worked on this project as part of a team, including myself, Sheikh Rabi, Buana Smith, Armando Navas, and Tara Rogan. So on that team, we've got soil scientists and mechatronic engineers and biogeochemists. So as a subtitle to this larvae as fertilizer title to the project, I want to really investigate this idea that if we feed the microbes in the soil, we may be able to synchronize the nitrogen supply with plant needs and achieve improved nitrogen use efficiency. One of our guiding principles here is this idea of synchronizing nutrient supply with the need of the plant to take it up. So probably most of us here would have an idea that nitrogen, conventional fertilizers tend to be highly inefficient. About 40 to 60% of the nitrogen applied in fertilizer forms tends to end up in the plants in common crop production systems, and that can be as low as 15% in some Australian production systems in wet years. So that's all about this effect where conventional fertilizer nitrogen supply tends to be highest initially after application and tail off in the season, whereas the actual need of the plant can be low initially for a seedling and increase radically as the season goes on. So they're almost exact opposites of each other. The techniques we've applied to study this type of these questions have included reaction vessel trials with ongoing real-time gas emission measurement and microdialysis, which enables us to see the forms of nitrogen in the soil. That image there is a reaction vessel with larvae in it, and see the fungal growth is actually a good thing in this case. And we also have growth accelerator trials where we're able to robotically scan the system and measure the dry matter production on a daily basis or a weekly basis so that we can see relative performance of different materials. And of course, we also conduct, and this is for an adjacent project, field trials. So added to that aspirational goal of synchronizing supply, there's the question of how we might do that. And this is one of the clues from about 2007, a quote from a paper which has really guided a lot of our work ever since. So this inefficiency is a consequence of the uncoupling of carbon, nitrogen and phosphorus cycles via the use of conventional highly soluble fertilizer forms. This results in agricultural ecosystems being maintained in a state of leaky nutrient saturation. Now, we've sought to solve that issue of leaky nutrient saturation in these projects to feed the soil microbes first, and I'll tell you why. Elaborating on that, we believe, it seems apparent anyway, that manipulating the ratios of carbon to the other nutrients, including nitrogen, we can influence biomass development, that's soil microbial biomass, the population of those organisms. We can also manipulate biomass nutrient utilisation and the release of nutrients. The idea being that we can generate a system where we have a sparing excess of N above the average nutrient ratios required by these soil microorganisms. And then we can enable the soil to turn those nutrients over as time goes on. So this is the results from the project that everyone's been talking about so far, but there's also some data in here you'll see from the Smart Farming Partnership project, which was completed for a number of industries. So that description of that project's in that bottom paragraph. Right, so this is a multivariate data analysis diagram, which you don't need to delve too deeply into, but the only thing is that ongoing nutrient supply is related to, we've found across a range of different treatments and soils, fertilizer layer, carbon to nitrogen ratio. So why is the ongoing nitrogen supply most related to that carbon to nitrogen ratio in that immediate soil surrounding the fertilizer? And we believe it's because there's a sweet spot for soil microbes. Here we have on the top left a soil where it's had every other nutrient added to it that it requires except for nitrogen. On the top right, the same soil system with a conventional urea addition. On the bottom left, an organic fertilizer product that's currently on the market added to that soil system. And on the bottom right, our modification of that to optimize the carbon to nitrogen ratio. Now, these are actually the average soil pots from a trial. So I haven't skewed this in any way. These are the average out of 5 or 6 pots. What I want you to notice that these two aren't doing too well. So if you use organic fertilizers in an uneducated way, you can get poor results. However, if you're prepared to take a number of things into account, your performance can be significantly better than urea. Now, why do I say that? The last couple of photographs coming up, you'll see here the performance of that modification is better than urea. So that raises a question, just how difficult was that to achieve and how uncommon is it? So let's just look at urea in this graph. This is one of our soils, a growth accelerator trial. That's our urea data for nitrogen uptake from 0 to 44 days, then later on in the season, and that's just the total. So this is where we have formulated the larvae up as a fertilizer, and a couple of our formulations, about half of them performed much better than urea itself. Likewise, this is a formulation of Future Green Solutions proprietary extract of the larvae, which gives you a higher nutrient density and a number of other advantages, and it's performed well in this trial as well. It's worth noting that actually there was a range of other treatments from other circular nutrient economy products that, if you formulate them correctly, can also perform better than urea. And in particular, for the audience we've got here today, I will highlight a couple of those for you. So these treatments here are all piggery sludge based materials. And these materials here are the sludge from the bottom of dairy effluent digesters, reformulated as a fertilizer. So they're not just raw, they've had a number of things done to them. This is a similar sort of study for a different soil. Note here that the second period of production, the second harvest, is significantly more important in this soil. So soils vary greatly in how they respond to fertilizers, I guess, and you can get more of this ongoing nutrient supply, and you have to tailor your formulations of fertilizers to match the requirements of soils. The other thing about urea N is that it really is extremely vulnerable to losses. This is urea here. You can see that it's as bad or worse than any other of the formulations we used in terms of nutrient leaching. Some of ours weren't too good either, but certainly if we're able to make formulations that result in lower losses of nitrogen in runoff or leaching losses, then we've got a much higher likelihood of ending up with better nutrient use efficiency, particularly in wet systems, wet production systems. So evidence actually is unfolding from our studies that soldier fly larvae, with their ideal sorts of ratios of carbon to nitrogen and some other good characteristics, and some of the other circular nutrient economy products, can be formulated in a way that they tend to promote biomass development, and then ultimately that's able to help us to synchronize N supply with plant need, decrease waterborne losses, so that's leaching and runoff, and improve nutrient use efficiency. Now, what that does is gives us higher residual nitrogen in the soil and a greater capacity of the soil to, on an ongoing basis, mineralize nitrogen. So you end up with systems that where you may have some losses through some adverse climate things like perhaps a leaching event, but your soil will be more capable of continuing to mineralize subsequent to that event than if you just use conventional urea fertilizer. That's why I say you build more resilient soil profiles and you can also retain carbon, whereas some evidence suggests that urea additions to soils can result in destruction of soil carbon. So urea performance is not impossible to beat, and we're continuing to work in this sort of area. Currently investigating with isotopes where exactly the nitrogen is derived in these systems so that we can optimize them for better and better performance. Thank you very much. And I believe it's Marit delivering the next presentation, unless there's questions.
Is that correct, Jeremy? Is it me next?
That's correct, Marit. Off you go. We'll deal with. There are a couple of questions in the Q&A, and we'll deal with them at the end of the webinar, if that's okay.
I'm just trying to find my document. I'd like to use the presenter view. There we go. Should be uploading now.
We're seeing your face at the moment, Marit. Not the
Yeah,
others.
it's uploading. It just always takes a while. I'm using my phone because my internet has broken down at home. Welcome everyone. My name is Marit Kracht. I'm an agricultural economist at the University of Western Australia, and I was involved in this research by looking at the low cost and feasibility of this potential product. So we were looking at sorry, the chat keeps popping up. It's a little bit distracting. My apologies. So we, in the socioeconomic research, were looking at two things. On the input side, the substrate side, we were looking at, are livestock farmers interested in using black soldier fly to manage livestock waste and manures? And what would be the potential barriers or opportunities from that input side, the provision of substrate? And on the output side, we looked at, who would be interested in using this potential black soldier fly derived fertilizer product or soil improver? And we had a team of people involved, including Vandana Sabroy, Fiona Dempster, and Faye Rola Robson, who are all in my Centre for Agricultural Economics. So we did a bunch of interviews. So socioeconomic research looking at barriers is a lot about interviews and surveys. We also did some modeling, like cost benefit analysis modeling. And interestingly, we did interviews with livestock producers looking at their interest in, using black soldier fly, and with potential end users. And there we focused on farmers, not on home garden, but on broad, on the wholesale market. When we tried to do a survey with livestock producers, unfortunately, we advertised it really widely, and it got picked up by people all across the world. And so we could no longer distinguish whether the answers we got were from Australian farmers, who is what the audience that we're interested in, or from maybe American farmers, or just random people who complete surveys for fun. So unfortunately, I can't show you any surveys for the livestock producers. The fun of doing research. So I'm going to go straight to the results section. So on the waste producer side, we asked people about the cost of their current livestock management, and then we wanted to evaluate that against the cost of using black soldier fly. And it turns out that there is very little information about the cost of the different components of managing livestock waste, like manure. There were, on the one hand, we were looking at what are the financial costs, things like You know, the management, the stockpiling, the collecting of waste, the transport of waste. How much does that cost, and can you itemize that? But also we were interested in the non-financial cost, things like odor or nuisance cost, potential impact on your the health of the people who handle these wastes, and greenhouse gas emission. Now, there's plenty of research on those non-financial costs that we could cite. On the financial cost, however, there's very little information. We gauged through the interviews and the survey that we did that, first of all, those costs are so variable for different industries. Even in the pork industry itself, which is what most of you may be familiar with, there is so many different systems that it was hard to classify how much it costs to manage livestock waste. And also, they're often not itemized. It's just cost of doing business. We don't know how much it is. So that was an interesting challenge. What we found, though, is that farmers are very interested in using black soldier fly for their waste management. They were really positive. So there was no inherent disgust or aversion to using black soldier fly. So that was really, really cool. However, the barrier may be the transport of waste to a facility, a black soldier fly production facility. So maybe we need to develop options for the on-farm application of black soldier fly to address some of those transport cost concerns, but also biosecurity concerns and regulation around what people are allowed to do with their manures and potentially carcasses, etc. So that's a next research step that we identified. Then we also looked, I'm now going to go to the end users, the potential end users, and we looked at whether there may be a market for black soldier fly fertilizer products, which are now available in the market. And some of these are even available in Australia now, but that's for the home market. And we were interested in the wholesale market, things like broadacre farmers, horticulture farmers, pastoralist or dairy farmers. So we made this survey that uses an economic technique called non-market valuation. So it's a technique that we use to assess, are people potentially interested in a product, even though it's not yet available in the market? And what sort of weight do they attach to different characteristics of this product? Because we wanted to know, are people just in general interested, or are there certain features of this black soldier fly fertilizer that is more important to them than others? So this technique is called a choice experiment, and you see here that we defined several features, potential features of this product, which came out of the biophysical research. Things like the carbon content of the potential carbon content of the product, and it ranged in percentages. The nutrient content of the product, typical fertilizer characteristic, but also we looked at different forms of the product, because different types of farmers use different type of fertilizer, and we want to know, should we focus on an encapsulated product or a granulated product, or maybe people are more interested in fertigation or fine particles. And then also we have a price, and we use that price to evaluate, okay, how much would people be willing to pay for this potential black soldier fly fertilizer? And then we present them with different options, and people see multiple of these questions, and they choose which one of these 4 options is their preferred option. And by doing, econometrics, which I won't bore you with, we can evaluate what's the weight attached to these different features, because these characteristics vary in each question. So to the results, again, we find really positive attitudes towards black soldier fly derived fertilizers or soil amendments. Whether it's a fertilizer or soil amendment really depends on the characteristics of the product. So we kept that broadly open. We did see that BSF fresh is unlikely to be able to compete with synthetic fertilizers that have a really high NPK content and they're specifically targeted at nutrient content. Also, it has a high bulk density, which makes it more expensive to transport. But it will be potentially competitive with organic fertilizers and soil improvers, which have similar characteristics in some cases. And farmers were really interested in that, also from the perspective that it's perceived as a product that will improve the sustainability of their business and the sector more broadly. So we then have a few results specifically for which of those features of the product, which of the characteristics are preferred. And we can see that preference through the econometric modeling, and people are willing to pay a higher price for those characteristics. So they preferred granular products rather than superfine particles or liquid particles, probably because most of the respondents to our survey used spreaders or air seeders, which is where granules fit directly. So you don't have to change any of your machinery. The organic carbon content of this product was really interesting to people, particularly when the carbon content becoming 20% or more. It then becomes this really clear soil improver product. On the NPK content, it ranged from very low to medium, which is realistic for this sort of product. About half the people really wanted at least that medium NPK content from a fertilizer perspective, but there were also about 50% of the farmers who didn't actually mind if it was a low NPK content. They would still use it as an additional fertilizer, but mostly as a soil improver. And the people who were most interested are those farmers who said, who we qualified as alternative farmers. And those were people that said, oh yeah, no, I'm not a conventional farmer, I'm a sustainable farmer. So it was a self-identification. And we'll get to the questions after the presentation. So to leave some time for questions, I'll finish up with saying that farmers, both from the substrate, from the input, waste manure input side, and from the potential end user side, were really interested in this technology. So I think there is definitely potential for this as both as a waste management technology and as a potential fertilizer production. So we now need to, the next steps in research from my perspective, from this socioeconomic perspective, is really to look at, can we maybe use this technology on farm to reduce, to avoid concerns with biosecurity and waste transport. And we need to work a bit on, what is the price at which BSF fertilizers will be put into the market, and that's going to be a market forces game of how much does it cost to produce versus how much are people willing to pay. But at least our research gives some information about farmers' willingness to pay. And finally, I've noted that was which was a part of our project, but a minor part, the need to develop regulation in this field. If you compare it to the European Union, everything is regulated. It's very clear what you're allowed to feed to your insects and what different potential users are allowed. But in Australia, this regulation is still developing, and without regulation, we are a bit in limbo of what we can do in terms of putting products on the market. And I'll end there. So could you stop? Yeah, stop sharing. There we go.
Yeah, thank you very much, Marit, for that. We've got a couple of questions in there, which I'd like the presenters to answer if possible. We've got a couple that were answered earlier in regard, which you can see in the chat there, that Luke's answered a couple of those questions, but there's a couple here that I'd like to throw to the presenters. Were any LCAs completed across the project? I think Sasha, you would touched on that briefly.
No, there was no LCA conducted. That was one of the things that I suggested as a further piece of work, because obviously we just tested the so the FRAS as its potential to reduce greenhouse gases, but we didn't check the whole production cycle.
Okay. The next one was NPK tested in the fertilizers? I think Luke, you did some of that, and also Sasha and Matt.
Yeah, we tested it. I can answer that because I looked at all the data to inform the economic work, and yes, it was. So the range that we include in our choice experiment is based on the range that was observed in the products.
Yeah,
and that varies with substrate.
We're comparing to systems where the thing we were competing against was urea, but in those systems we had optimized the P and K by adding those as well. So there's systems where the only variables were carbon and nitrogen was what we're trying to target, which meant we had to juggle the other concentrations of the other things. So
that was one of the other questions as well that came up about the carbon to nitrogen ratio, and what was it?
Yeah, so the materials we're using across those two different trials ranged in C to N ratios from 0.5 to so that's C to N of 0.5 up to about 11. But you've got to take into account the carbon ratio, the soil as well. So it's the soil in that zone that makes the most difference with those additives in it. So the range there was from 9 up to 13. So that should give you an idea. It just so happened that if you want to extend out the period of supply so that you're getting turnover over a longer period of time, the higher the carbon to nitrogen ratio, the longer that takes. So it's not the answer of what the optimum is depends on what your production system is and when you want the nitrogen delivery.
Excellent. Was there any work on identifying beneficial microbes or chitin concentration?
We've done a heap of metagenomics on the samples, and we've done beneficial microbes for other work, but for this one, it wasn't clear which particular group, that there was any sort of, what would you call it, plant growth promoting microbial activity from individual sets of organisms. It was more about the turnover of carbon that we're getting in these particular sets of experiments. That's both the Smart Farms project and the Soldier Fly project. So it's more about the substrate and the group of organisms that are already in the soil rather than an inoculant effect in our case. I can't speak for the other researchers who are using FRAS.
Yep, I'll just do this last one here from Phoebe, and then we've got another one. What were the theorized mechanisms for increasing crop or plant drought tolerance?
That was actually that was mine, but it was the last bit of work that was done. So we're actually still analysing that data set. But one thing that has come in is that we do see an increase in some microbes that are involved or have been known to help aid the plant in protecting the plant against stress tolerance. So it could be a microbial effect, but we're still, as I say, we're still getting through some of that data set now to really write that up. And we also saw some beneficial microbes in the FRAS, and it did seem, well, it looks like they are, well, one of them at least seems to be surviving into the soil.
So did you establish an impact of that, Sasha?
No, that's again further work, and I think that's something I need to discuss with Luke where he wants to go next. But we also saw it with fungi, which was kind of very exciting.
Yeah, fungi is pretty interesting that you get with the larvae because it's they're sort of slow turnover organisms generally, and that's a potential benefit if we're trying to tailor delivery. And a substrate that really generates fungal activity is pretty interesting.
And I just want to say from this project, there has been a final report, and there's fact sheets and journal articles and things like that, but they're just going through the approvals process with the Commonwealth at the moment. There's also some information on our Communities of Practice page on Black Soldier Fly as well. So I just wanted to just mention that there will be some resources coming out of this project at the end of it. They're just going through that approvals. We've just got time for another couple of questions. Hopefully this is not going to finish dead on.
There's one from Phoebe
Yeah.
there. So
can we go to someone maybe like Charles? We've just been doing lots of Phoebe's questions. There's
I
some
was
here.
just going to go to what characteristics determine whether it is classified as a fertilizer or soil amendment.
I think that's probably more your expertise, Janine. I think we see something as a soil amendment if it's something that improves the soil structure and the carbon content of the soil, and more as a fertilizer if it's more targeted at that nutrient addition. I don't know if there's a formal distinguishing feature between those two. I think it's more the terminology that we use to distinguish between products.
Exactly, and we did do a review and also a fact sheet on the different states and their determination of when a waste becomes a product or whether it's not classified as a product, and whether it's got any additional regulations in relation to that, and whether it's more likely to be treated as a compost or more likely to be treated as a raw manure. So we will have a fact sheet coming out on that as well.
There's an interesting question from Charles about pig broiler manure is an excellent fertilizer. Doesn't this add an extra step? So what do we think of that?
Who do you want to answer that? Well, no, because it might be an excellent fertilizer in some situations. So if you've lucked out and got the right carbon to nitrogen ratio, and you've got a number of other characteristics that suit that particular system, that's just luck. And yeah, I know sometimes sludges and so forth perform really well, and they can have plant growth promoting rhizobacteria and so forth in them. But to actually time after time produce those benefits reliably across different industries, we have to have better understanding than that. And so that's what we're deriving here, so that we can use these materials to produce highly efficient, demonstrably superior products that have high enough value to have a wider economically viable transport radius.
There you go.
That's probably our biggest cost. Our biggest cost from manures is transporting moisture. So, and transporting volume in terms of getting benefits off farms, which as a lot of us know that especially pig farms or smaller intensive livestock industries were designed to have a reuse area of around 20 years. And a lot of the time that's now becoming quite nutrient rich. So to be able to move some of these products off site, it is quite a benefit, and also reduce the handling, the cost and the labor associated with raw manures.
Yeah, also making it possible for people who need to apply the nutrients in a more precise way so that they can deliver them with an air seeder directly where they want them, instead of broadcasting them so that you get a pretty spotty application across the paddock. That's just the purely physical stuff can be very, very beneficial.
Yeah. I think we've just gone a little bit. Oh, here we go. We've got one here. We already have adequate legislation in Australia for the feeding of animals with insects. What needs to be changed? Oh, we've got a comment here.
Well, it's because the feeding of animal with insects is not the only aspect that we're looking at here. We're also looking at, can we use substrate? Can we feed the waste and the different types of livestock waste to the insects, about which there is regulation in the EU, and in some cases it is allowed, in some cases it's not, because they're production animals in the EU. But also, can this be used as a fertilizer or soil improver? And as there is no classification for that product for a BSF derived fertilizer yet in every state. So that's another regulatory aspect that needs to be developed.
Yeah, and we did do a bit of a review on the biosecurity risks, and also in relation to restricted animal materials, and what Animal Health Australia classes restricted animal materials, even though it may have gone through a transformative stage, they still need to look into that in more further detail as to whether it's classed as RAM. At the moment, it's case by case that they'll kind of look into it, and it has been raised with them as well. So that's just another aspect that we need to consider. So yeah. We've got another one here.
There's something about heavy metal accumulation, which has been observed in other studies in the EU. I don't remember whether we also looked at that.
We did look at heavy metal accumulation. That's what our vets looked at. I don't think they did. Luke, you probably can remember better than I can, because that was, the veterinary side of it.
With most of these things, it's tied back to the substrate, particularly feed products used. So some of the industries will have higher zinc loads, and aluminium in particular. We saw across the board in some of those industries. I think from memory, the pork industry was quite high in zinc, noting that that's part of their feed components. And yeah, I'll have to take the other ones on notice, because I don't want to cross my heavy metals and industries.
Yeah, and that's the thing. One of the feeds in pork, especially for weaners, is products that are high in zinc. So that usually translates through all of our manure products, whether it's raw manures or frass or anything like that. And we've always said to people, there is restrictions on how much heavy metals can be put out onto the soil, but we always say to people, well, look at your soil test and adjust your fertilizer to what you need. Some soils actually need zinc, so it's actually a really good product. So as long as you keep an eye on what's going on in the soil, I think that's it's quite good to have a bit of an understanding of what's in the product and what's in the soil and how those interactions go. So we always recommend, when you're putting on any products, to work in accordance with your agronomist, who can make sure that the crops are getting exactly what they require, and the soils as well. If there's no more further questions at this stage, there's a few that have been answered in the chat there, but as we said, this will be recorded so people can have a bit of a look. Or if you've got any specific questions, feel free to contact any of the researchers or anyone that's been involved in this. But yeah, I'd just like to say thank you to all the researchers for providing that information today. And yeah, if you've got any further questions, please feel free to contact us. And yeah, we should have some resources available in the near future once it's all been approved.
Yeah, and thanks to the funders too.
Yeah, thank you to the Commonwealth and all the contributors and the funders. Yes.
Thanks, everyone.
Thanks a lot.
Great to see you here today.
Thank you. Thanks for your time.
Thank you.
Thank you very much, everybody.